Okay, welcome back. Today, we're going to talk about Chapter 9, which deals with hypothesis testing. Now, hypothesis testing is very, very similar to confidence intervals, which we covered in Chapter 8. The big difference is that for a confidence interval, all we're trying to determine is a certain range where we believe the mean might be. In hypothesis testing, we're taking that one step further, and we're trying to actually support or reject a certain claim that the mean would be affected or not affected by some kind of change, or whether or not a reported mean is actually accurate. Let's go ahead and define this, and then we'll get some concepts. We'll end with a couple of examples. So, hypothesis testing. Suppose we think that a population has a certain mean, and then we took a sample, and we found the sample has some other mean. Maybe this mean is off by a little, maybe it's off by a lot. Hypothesis testing allows us to support or reject the claim that the supposed mean mu is reasonable based on the results from our sample. Always what we're going to do here is set up two conflicting hypotheses, a null hypothesis and an alternate hypothesis. And the idea is that these two are going to be either one is true or the other is true. Never both, never neither. Might be something like the null hypothesis says that the mean is larger than this number, whereas the alternate says that it is less than this number. You can't be larger than or greater than. We'll always assign equals to the null hypothesis. That way we cover all of the different possibilities. So that's the idea, is that the two hypotheses together cover everything that could possibly happen. Either one is true or the other. The null is going to be kind of the default, and the alternate hypothesis would be that something is different than the default. We're never 100% certain based on our sample because it's just a sample. It's not the whole population. And so we don't say the null hypothesis is true or the null hypothesis is false. Instead, we will support or reject the null hypothesis. Or we might say we fail to reject the null hypothesis. Now, always the hypotheses when we're doing a problem with calculations will look like an equation. The null hypothesis will say something about the mean, and the alternate hypothesis will say something different about the mean. In this case, mu is the variable that we use to represent the population mean, and m would be some specific number. Maybe m is 7, and that's the specific mean that we're trying to test against. You'll notice that in both of these, we've got two different expressions. On the left-hand side would be the null hypothesis, and it always includes equals inside the expression. So we could say the mean is equal to a number, greater than or equal to a number, or less than or equal to a number. The alternate hypothesis is always the exact opposite, so it never contains equals. If the null hypothesis says we're equal, the alternative hypothesis says we're not equal. If the null hypothesis says we're greater than or equal, if the null says we're greater than or equal, the alternate says we're less. Whereas if the null says we're less than or equal, the alternate says we're greater. So we will always include the equal sign on the side with the null hypothesis. And the alternate hypothesis will always include the not equal sign. Each of these three would look a little bit different when we're creating a graph. So let's go ahead and set up the three equations. The mean is equal to some number. The mean is greater than or equal to some number. And then the mean is less than or equal to some number. Always in the graph, that number would go in the middle. And then we'll construct essentially a confidence interval, which we know involves shading regions far away from the mean at a certain percentage. We've got the alpha over 2 going on. The difference is, for an equal sign, it works exactly the way we're used to it working. But when it would be greater than or less than, we're only concerned with unusual results in one direction. So for example, if we think that the mean is greater than or equal to some number, then very large results are not weird. It's only very small results that are weird. So we would only be shading one side. And in this case, we will only be shading the other side. A good way to figure out where you're supposed to shade is we shade the part with the alternative hypothesis. We shade the part that we're not expecting. The null hypothesis kind of like the default, and the alternate hypothesis would mean that something's different. So we shade the part that might be different because hypothetically there should be a really low chance that that would happen if everything was normal. So if we're saying that normally the mean is equal to some number, then it would be very weird if it was high or low. Whereas if we're saying normally the mean is greater than or equal to some number, it would be very weird if we got a very low number. But a high number would not be weird. That's expected by this expression. Similarly, if we expect it to be very low, then it's only weird if it's very high. So we only shade one side. In both of these setups, the amount that we shade is the full alpha, since we don't have to split it in half to go on each side. We would call this a two-sided test, and we would call this a one-sided test. Now, let's do a couple of examples with determining what the null and alternate hypotheses are and sketching diagrams. So suppose that we want to test if the mean height of 8th graders is 66 inches. The null and alternate hypotheses. Here it just says is 66 inches. So that sounds like our null hypothesis, that the mean equals 66. The alternate would be that the mean does not equal 66. Again, remember, whichever one contains an equal sign, that's our null, and whichever one doesn't contain an equal sign, that's our alternate. In terms of a graph here, we would have a 66 down the middle, and then we would want to shade both sides. Again, you're shading based on the alternate hypothesis. It would be unusual if the mean was not 66. A high or a low value would make that unusual thing happen. So we'll shade on both sides. Just like before, alpha, which is kind of like the confidence level, would have to be given to us in the problem. Let's do one more like this. Coke claims they fill every can with at least 12 ounces of liquid, and we want to test this claim. We need a null and an alternate hypothesis. At least 12 would be greater than or equal to 12. Notice we've got an equal sign, so that will go with the null. Therefore, if it's not greater than or equal to, it must be less. That's the alternate hypothesis. If I was sketching a distribution here, of course, put 12 in the middle. We want to shade the part with the alternate hypothesis. That's the very low end. In this scenario, we would not split alpha into 2 like we would with confidence intervals. Now, the idea of this type of thing is that we are only a certain level confident. Remember, we're talking about 90% confidence intervals, 95% confidence intervals. Well, with hypothesis testing, it's the same thing. We want to be as sure as possible. We can sample more people, more of whatever we're doing in order to become more certain, but we're never going to be exact. What error deals with is it deals with the chance that we are wrong in either direction. And there's two ways we can be wrong. Either the null hypothesis was true, but we said it wasn't true. Or the null hypothesis was not true, but we said we didn't think that it was wrong. We said we thought it was fine. These are called respectively type 1 and type 2 error. And there's a couple of ways to keep track of these. The first would be false positive and false negative. In type 1 error, you are saying that something unusual happened when in reality, nothing unusual is going on. That's false positive. Whereas with a type 2 error, you're saying that nothing unusual is going on, but in fact, something unusual is going on. And that would be type 2 error. Sometimes one of these is worse than the other. It all depends on the scenario. The way that I was taught to remember this was to think about Jesus. Jesus, the null hypothesis for everyone, but for Jesus in this specific scenario, is that you are innocent. And the alternative hypothesis is that you are guilty. This is how court works. You're innocent until proven guilty, so the null hypothesis is innocent, and the alternate would be guilty. Now, regardless of what you believe, following the story from the Bible, it says that Jesus was innocent, but everyone believed, or at least the crowd believed, that he was guilty, and so they killed him. This is type 1 error. The null hypothesis was true, but they rejected it. They believed he was guilty, and they killed him. Now, Jesus, again, whether or not you believe this is true, according to the Bible, Jesus was a pretty good guy. He was a type 1 guy. So that's type 1 error. Is when something, the null hypothesis is true, but we reject it anyway. To remember that, think of Jesus. Type 2 error would be the opposite. This would be that if somebody was guilty, we said, you know what, they're actually not guilty, and we let them walk free. In a court of law, type 2 error, obviously not great when we let criminals walk free, but type 1 error, way, way worse when you convict an innocent person. So in the court of law, we try to make it so that the type 1 error is as small as possible because it's very, very bad. We've got variables that we use to represent the different types of error. Alpha is the probability that we commit type 1 error. And it's the same alpha that we have previously. It's the part outside of that center region, the part that we shade. Alpha in this case means the same thing, it's just different words for the same idea. Beta is a new variable. We're not going to learn how to calculate it in this class, but it's the probability that if the null hypothesis was false, then we don't reject it. It's the probability that we commit type 2 error. Sometimes you want to make alpha as small as possible, and sometimes you want to make beta as small as possible. Usually you want to find a good balance between the two, but there's usually one that is much, much worse. Let's go through a couple of examples here. Let's suppose that the null hypothesis is that Frank's rock climbing equipment is safe. Now, in these examples, we're not going to have equations that we can make, and so we wouldn't have actual computations to do. We can still think about the idea of error. The null hypothesis is that the equipment is safe, and the alternate would be that the equipment is not safe. Now we can either have type 1 error or type 2 error. Maybe this would be a check that the rock climbing safety people did on the equipment before sending Frank up to go climbing. Type 1 error would be that the null hypothesis is true, but we reject it anyway. The equipment is safe, but we tell Frank it isn't. Type 2 error would be that the equipment is not safe, but we tell Frank it is. In this scenario, type 1 error is mildly irritating for Frank. He thought he was going to go climbing and said he has to go get his equipment fixed. That is a day lost. Maybe he had to spend some money that he didn't need to. A little bit obnoxious. But type 2 error, Frank goes climbing. Frank probably falls off the wall. Frank has a very bad day. In this case, type 2 error is way worse than type 1 error. So if I was examining Frank's equipment and something looked a little bit off, I would probably go to Frank and I would tell him, I think your equipment isn't safe. I think you should get it checked out. Let's do one more example like this. Suppose the null hypothesis is that a patient does not have a disease, so is not sick. And the alternate would be that the patient is sick. Maybe we have some kind of blood test that we're doing to determine whether or not the patient is well. And we know that in this certain disease, it has elevated levels of the thing we're testing for. So if the levels are very high, we think you have the disease. But maybe the person's levels were high for some other reason. Or maybe they weren't that high, and so we thought that they didn't have the disease. So that's what this error is looking at, is that the results of the test don't match up with the reality of the world. For type 1 error, that would say the null hypothesis is true, but we reject it. Patient not sick, we say they are. Type 2, patient is sick, we say they aren't. In this scenario, again, type 1 error, not that big a deal. We tell you you're sick. Obviously, it's an emotional time, but then you get tested again. After going through some small amount of treatment, you realize that you were actually fine all along. Sure, some medical bills, not great, but you're okay. Type 2 error is a disaster. The patient is sick. We say they aren't. They go home. They don't get any treatment. The disease gets much, much worse. When I am looking at my blood test, if the levels are just a little bit high, I should say, you know what? Let's play it safe. Let's assume they have the disease until we can prove otherwise. Because of how bad the type 2 error is, that's how we should set up the test. So when you're setting up your test, you're always thinking, which of these scenarios would be much worse? And choose your alpha level accordingly. The larger that your alpha level is, would be more chance of type 1 error, but less chance of type 2 error. Normally, we'll give you an alpha to work with, but it's something to think about if you were setting up a test of how large you would want your alpha to be. We've already talked about one-sided and two-sided testing, which is the last big difference that we need. When you see the greater than or less than sign in your null hypothesis, you know it's going to be a one-sided test. And we have to remember that we're only going to be shading one side. The whole alpha is on that side, so you need to remember not to divide it by 2. For this reason, I strongly, strongly recommend to draw your picture, sketch your distribution every single time you do one of these hypothesis tests. By drawing the picture, it'll be less likely that you forget to do one of these steps and leave out a piece. Now, here is the process for using confidence intervals to perform hypothesis testing. It's all that we've been doing up until this point, just with a little bit of extra before and after you set up the confidence interval. First thing we do is state the null and the alternate hypotheses. Usually we'll want to write the equations. You can write it in words too if you would like. Next, we need to determine whether we're doing one-sided, which remember is either greater than or less than, or two-sided, which would be equals. For one-sided, we use the entire alpha. For two-sided, we use alpha over 2. Remember, this is what we've already been doing, whereas using the whole alpha is different. So make sure you keep that in mind. Drawing the picture will help. Step 3, absolutely nothing new. It's exactly what we've been doing up until this point. Write down the variables, sketch the distribution, determine whether we're using our Z or our T scores, whether we're doing a proportion, and then do all our calculations using Google Sheets. We'll get a ZT score, standard deviation of X bar, we'll get an EBM, and then we'll get a max and a min value. Then we'll come up with a conclusion. Accept or reject the null hypothesis. And this deals with, is the value in the shaded region, or more specifically, outside the interval. We're going to be given some mean that we think and then a resultant mean from a sample. If the mean from our sample is in the interval, we do not reject the null hypothesis. If it is outside the interval, we do reject the null hypothesis. And finally, we interpret the results, which is just a quick sentence stating, based on the results of our exam, what happened. Let's go through 3 examples so we can see what kinds of different hypothesis tests we might end up doing. Test number 1, statistics students believe that the mean score on the first statistics test would be a 65. The instructor thinks no, the mean score is higher than 65. So he samples 10 scores, finds from this sample a mean of 67, a standard deviation of 3.2. He's going to do a hypothesis test using a 5% level of significance. Now, let's switch over here. We're going to want to be looking at Google Sheets here. So let's zoom out, give us some space, and let's set up what we can. First thing we need to do is we need to state the null and the alternate hypotheses. It looks like we're comparing the mean to 65. This is what we think that the mean might be. For the null hypothesis, it says that is 65, whereas the instructor thinks that it is higher. So our null hypothesis would be that the mean is less than or equal to 65. And the alternate would be that it is larger. Because we saw higher, higher is not greater than or equal, so we knew that one had to be alternate because the null hypothesis always contains the equal sign. Okay, so then we know we need to do a one-sided test. And we're going to sketch our distribution here a little bit earlier than we normally would. We've got that mean of 65 in the middle. We're going to be shading for the alternate piece. So we're going to shade up here. Unlike with a confidence interval, because it's a greater than, we're only shading on one side, not both sides. So this part should be the entire alpha. I'm going to, for the moment, just put alpha equals and leave it as a blank, and we'll write that down once we've got our information. We can get that all now. Let's see what we can find. We still don't know what the real mean is, but we can put an arrow over to the hypothesis tests because we have a guess of what the real mean is. So we're not kind of shooting blindly anymore. We have an idea, but our idea might not be correct. We have a suspected mean. Our X bar was 67. The 67 is not going to be the center of our distribution. It's going to be somewhere over here. If X bar is here inside of the shaded region, or I should say closer to the mean, that's a normal result. Whereas if it's over here, that's an unusual result. And that will determine whether we accept or reject the null hypothesis. So that's what we're doing here with the X bar. We've got a standard deviation. It looks like it's from the sample. It says samples 10 students and finds a standard deviation. So we don't know the real standard deviation, but we do know the sample standard deviation is 3.2. Remember, that means T-scores. Our sample size is 10. Since we're using t-score, we also need a degree of freedom, be 9. And the alpha is this level of significance, 0.05. Let's fill that in our graph. Now, moving over to Google Sheets, we need to find a standard deviation. Actually, let's start with the t-score for alpha. Then we'll need a standard deviation for x bar. We will then find an EBM, x min, and x max. Now the t-score, unlike normally, we are not dividing by 2 because it's a one-sided test. We only want to use the regular alpha. So equals t inv of 0.05. Our degrees of freedom is 9. So that'll be 1.833. Remember, the t inv needs a dot, and I got a negative value, which means I remember to use the correct formula. Next, I need my standard deviation. We're going to take the 3.2 and divide by the square root of 10 to account for the fact that it is a sample whose standard deviation we want to look at. Gives us 1.01. For EBM, we'll multiply these two together. I'm going to include a negative sign to flip the t-score. And then we can find an x min and an x max. So the mean that we got was 67 is what we're working with. And 67. Or whoops, sorry, 65 is the one we're working with. 65 minus this and 65 plus this. Again, we're working with the believed mean, the one that we wrote down in our hypotheses. So we found that the x max is 66.85, which means that the mean from our sample, x bar, is up here above. Let's go ahead and write that in on our graph real fast. So here, the x max was 66.85. And here, the sample mean x bar was 67. This was larger, outside of the expected range. In other words, what we're saying is there's less than a 5% chance that this would have happened by mistake. And so we will, in step 4 here, we reject the null hypothesis. Interpreting this, what does that mean? Based on this sample, we believe the average test score is higher than 65. Let's recap everything once more. We had a thought that the test score average was 65, and the instructor's belief said, I think the test score average is higher. We took a sample and we got a mean that was higher than 65. We need to figure out how weird it is. So we created a confidence interval. Because it's only one-sided, because we had suspicions only about it being very high, we only shaded one side. Performing our confidence interval, we found the EBM and then the min and the max, and we compared our value to see if it was inside of the interval. Because it was outside the interval, we said, you know what? I think that this would not have happened by chance if the mean was really 65. So I think the real mean is higher. And the result of that is rejecting the null hypothesis. Let's do 2 more examples here. Jeffrey, a certain 8-year-old, established a mean time of 16.43 seconds when swimming 25-yard freestyle with a standard deviation of 0.8 seconds. His father, Frank, thought that Jeff could swim the 25-yard freestyle faster when using goggles. So we bought him some fancy goggles and timed him 15 additional swims. For the 15 swims with goggles, the mean swim time was 16 seconds. And Frank is saying, I think the goggles help Jeffrey swim faster than his regular mean of 16.43. We want to conduct a hypothesis test. It gives us the alpha of 0.05, and we're assuming that the distribution of swim times is normal. So let's go through it all again. We want to write down the hypotheses. Null hypothesis would be that the goggles had no effect, and the alternate would be that they did have an effect, because we're trying to claim that with the goggles, the mean is less than 16.43. We're saying these goggles sped him up as compared to what he used to be able to do. So then the null hypothesis would be, nah, it didn't really change anything. These goggles are not worth my time. We should return them. So then we need to figure out if it's one-sided or two-sided. In our distribution, we'll sketch the alternate hypothesis, which is one-sided. Here's our alpha over here. We can smack on the 16.43. We know that the 16 is going to be somewhere in here. We just need to see, is it in the shaded region or no? The shaded region is the reject region. It's the alternate hypothesis region, and that's what we need to figure out. Let's write down everything we know. The suspected mean we don't know, but we have a guess. The mean from our sample ended up being 16. This time, the standard deviation is 0.8 seconds. That's not from our sample. That's the old standard deviation that Jeffrey had for his original swims. And he's been swimming long enough that we can believe that was a real standard deviation. So we'll say the true standard deviation is 0.8 seconds. That means we're doing z-scores. Sample size was 15 swims, and the alpha is 0.05. Put that in over here. Okay, let's do all our calculations. We need now a z-score for alpha. So we'll do norms inv of 0.05 gives us negative 1.64. Remember, we're not dividing it by 2 because it's a one-sided test. Standard deviation, we'll take the 0.8 divide by square root 15 gives us 0.206. EBM, we multiply these two numbers, and I'll stick a negative on to account for that. Then we're comparing this to the original mean. So we'll take the 16.43 minus the EBM and the 16.43 plus the EBM. Okay, that means that this border right here, the X min is 16.09. Our 16 is just a little bit less than that. So we will say that we reject the null hypothesis, which means based on this sample, the goggles do reduce swim time. In other words, based on this experiment, we are fairly certain that these goggles were a good purchase. They helped swim faster, and we should keep them. Let's do just one more example here. June believes that 50% of first-time brides in the United States are younger than their grooms. She performs a hypothesis test to determine if the percentage is the same or different from 50%. We sample 100 brides, find 53 they are younger than the grooms. We want to determine at 1% level of significance if June is right or not. Now, we'll do all of the same steps. We've got a null and an alternate hypothesis. In this case, I'm looking, I don't see anywhere where it says that June believes that it's more or less than 50%. She just thinks that it might not be 50%. So we don't have a greater than or a less than that we're working with. The null hypothesis would be that the mean is 50% or 0.5. And specifically, not the mean, but the proportion, because we're dealing with a percent. And the alternate would be that it's not. We'll sketch a graph here. With the 0.5 in the middle. And notice here, now, because we want to shade the alternate hypothesis, that's both halves, which is going to be alpha over 2 on each side. This is more like our confidence interval. We're going to shade both sides because we don't have a suspicion whether it's high or low. So we need to account for both. That means that our interval is going to be a little bit wider to account for the fact that we're not certain if it's very high or very low. There's a little bit of uncertainty in there, and we'll account for that by widening the interval, splitting the alpha up on each side. Next, we'll make our confidence interval like always. We see we've got a proportion here. P is going to be the unknown, but the P that we got from our sample is 53 over 100, or 0.53. So it was a little above average. This means that our Q that we got was 47 over 100, or 0.47. We also could have subtracted the 0.53 from 1 if we would have preferred. We have an N value of 100. And we can find our standard deviation with square root NPQ is the formula. That will give us 100, 0.53, 0.47. So let's go ahead and plug that in here for our standard deviation. 100 times 0.53 times 0.47. For the z-score, it needs to be for alpha over 2 now. So we'll use, remember, always norms when we're dealing with a proportion. So norms inv for our alpha over 2. We never actually wrote that part down. Alpha is equal to 0.01. So the alpha over 2 is 0.005 because it's a 1% significance. So 0.005 for our alpha over 2. EBM, we will multiply these two, accounting for the negative. And then we will add and subtract this from the mean. Remember, we need an extra step where we're going to do EBM for our proportion, where we take this number and divide by the sample size. Because we don't want an error for samples of 100, but we want an error on the proportion. So our x min will be the 0.5 minus this, and the x max will be the 0.5 plus this. Okay, so in this scenario, this right here is the x max, of 0.628, and this is the x min of 0.371. Our experiment gave us 0.53 as the suspected proportion. That is well inside the range. It's not in the shaded area, it's in the regular middle area. So we do not reject the null hypothesis. What does that mean? Based on this sample, we cannot say the mean is different than 50%. We can't say that it is 50%. We have no idea. But we don't have enough evidence to say that it isn't. So that's why we're not saying that we proved the null hypothesis or even that we support the null hypothesis. We're just saying we can't reject it. We don't have enough evidence to the contrary. If we really wanted to be certain, maybe we should do another test with a much larger sample. Eventually, we would come up with enough information to make a statement. But in this class, all we're going to talk about is supporting the rejection of the hypothesis or not rejecting the hypothesis. That's all we've got for today.